So today let us discuss about design of a two seats light sport aircraft. In the previous sections we have discussed about all the process which are involved in the aircraft design from overview of the design process. The next we seen about airfoil selection, wing geometry, thrust to weight ratio, wing loading, initial sizing, and we have special considerations, and we have a crew station, passenger, payload, aerodynamics, structures, flight mechanics, all the things we have discussed in the previous section. Today we are here to discuss about the two-seater aircraft, light sport aircraft, how to design an aircraft by taking up an design example. Okay, so in this what happens, so in this introduction just look into it how the process goes. Leonardo da Vinci once wrote, nothing is wanting and nothing is superfluous as the contemplating on the flying seagulls. So in the early history of flight, humans have the thought that dream of flying can only become a reality if they are able to imitate the birds. They have a concept. So already when in the ornithopters, we have a different, when we look into it, when the birds are flying, so that is the thing. If they imitate the bird, then only we can fly. That is the one concept what it is there in the olden days, that a human have a thought that dream of flying can only become a reality if they are able to imitate the birds. The idea of flying for recreational has emerged in the very beginning in the first human successful flight, that is 1903, that is Orville Wright brothers. Not from this, in this Orville Wright brothers we can have a record, but before we have a, when you look into a Vedas and Upanishads, we have that is a Bharadwaja Muni. He was given that the exact structure of an aircraft and how those things are like it will be affect to the system and how the flying will be there, how the different type of aircrafts we can see, how the different type of engines with 32 components by comparing with the human organs. Okay, so however, due to the many reasons such as economical and immature technology, this dream is not necessarily come true until the last few decades. So because in the last few decades it has not come true, but the design of airplane has changed, evolved significantly since in Wright brothers era. So it was became significantly successful in the Wright brothers era, where we can witness the evolution from the strut and wire biplane to highly sophisticated smooth fuselage jet engine aircraft. So what is that? The evolution from the strut, wire and biplane, highly sophisticated. You can see that what type of aircraft it is. It's a wire strut and wire biplane. We can say biplane, you can say up and above, and we can have struts which are connected to the from the upper and the lower wings. So when you look into Orville Wright brothers aircraft, you'll come to know that clearly how it looks like. The complete aircraft design process consisting of three distinct phases. So in the previously we discussed about it. One is conceptual design, the preliminary design, and detailed design. Okay, the design process commonly starts with a specific requirement sets forth either by potential customers on the desire to implement innovative ideas and technology. So design requirements contain several parameters such as aircraft range and payload, takeoff and landing distances, speed requirements. So these are the design requirements. What are those several parameters? One is range of an aircraft. What is the payload capability of an aircraft? So takeoff and landing distances. What is the distance of takeoff? What is the distance of landing? So and speed requirements. What should be the speed is required to attain the takeoff, the approach speed. So whenever you are coming for landing also, what should be the speed? So according to that, we have 1.22 times of the Vstall, 1.3 times of the Vstall, what we have seen in the, during the landing as well as during the takeoff condition. So usually the conceptual design contains 7 important tasks. So at the end of the design process, the overall shape, size, weight, and performance of aircraft are estimated and ready to proceed with the next design phases. So we can see here in this the project brief. So when you look here in the project brief, we have in this flow chart, it will explains us how the process goes. The first one is the requirement. We will take up the requirement from the customer, and next we will do the crude weight estimations. So we know that what is the weight estimations? We have a total design gross weight, that is W naught is equal to, we know that crew weight, passenger weight, payload weight, and next we have a fuel weight and as well as empty weight. These are all the different type of weights. It's a crude weight estimation. So crew weight and also we have a payload weight. It will not be, cannot be changed, so therefore it will be fixed, and only the we are doing the weight estimations, that is fuel weight estimation as well as empty weight estimation. From that we are going to do the estimations and we are getting up the weight estimation process. So next is critical performance parameters such as maximum CL, L by D, like if you have a wing loading and as well as a thrust weight ratio. So this is the airfoil selection when I'm doing up. So these are the performance parameters which are affecting on the selection of airfoil. So accordingly, when you select the airfoil, so next process we goes with a lift to drag ratio, that is called aerodynamic efficiency. And when you speak about wing loading and what type of wing should be considered, and it may be swept back, swept forward, it may be at like we have anhedral, polyhedral type of wing, and we have a delta wing structures. We have a swept forward, we have a different type of wing configurations we have seen in the previous sections. And also we see that configuration layout, the configuration layout. So when you speak about, we have the configuration layout and lofting process, we see that. So what should be the configuration? We have tell the two-seater, two engine, we have a swept back, it may be low wing. So what type of winglet it is? These are all of the configuration layout what we are going to speak. And also we spoke about lofting process. We spoke about lofting process. What is the lofting process? It is a mathematical modeling of an outer skin of an aircraft. It is called as a lofting process. And once it is done, we are going for a better weight estimation. And next we are learning for, we are going for a performance analysis. Next we are going for a optimizations we are doing up. And next with the iterative process. You can see that critical estimations we are doing L by D, W by S, T by W by using a Brickwatt range equations and Brickwatt endurance equation. L by C, V by D, ln of Wi by Wi minus 1. So the endurance equation also we are looking into it. So on the basis of that, we are doing the iterative process, and then you are going for a preliminary design process. So this is all the system of things which are taken in a conceptual design process. Once it completes, so when the optimization is told yes, then we are going for a preliminary design process. This is the steps which are involved in the conceptual design process. So when you look here, in this we can see that in this chapter, we represent the conceptual design process of a two-seater light sport aircraft. For ease of reference, we called aircraft as ZA230. We are giving a one name. So for example, each individual have its own name. You can give your own name. For example, Ashish light sport aircraft, Pooja light sport aircraft. So accordingly, what happens, we can give according to that. And also Arun Kumar, it may be like in the same way we can give out the different names, whichever the name you can name your own aircraft when you're going to design. And the project starts with a requirement in the given table 1. So these are the requirements for that particular aircraft what we are going to design. So one is maximum speed. What is the speed of an aircraft is 120 knots, and we have a range is 340 mile, service ceiling is 20,000 feet, and stall speed is 40 knots, and we have a landing distance about clearly 50 feet obstacle, takeoff distance is a 50, clearly 50 feet obstacle clearance. These are all the different types of requirements what it is required to build an aircraft. Okay, after this taking up a requirement, so we are going for a first weight estimation. That is the first weight estimation. We can see that the first weight estimation or crude weight estimation is based on the available statistics for the existing or ever built light sport aircraft, that is LSA. Here we want to see the trend of the weight of for this aircraft. The gross weight is built up, that is W naught, of the aircraft consisting of a crew weight, that is WC is a crew weight, W suffix P is called a payload weight, and W suffix F is called as a fuel weight, and empty weight. Summarizes what is that we have this equation we have seen the previous also, that is total design gross weight is equal to crew weight plus payload weight plus fuel weight and empty weight. So therefore, so what happens here, WC plus WP we cannot change, crew weight and the payload weight we cannot change, only the fuel with respect to the total design gross weight changes, and empty weight with respect to the design gross weight will be changed. So therefore we are making up a fuel weight estimation as well as empty weight estimation. Okay, so therefore WC and WV by W0 are already known, so we have to estimate fuel weight estimation based upon that. So we have seen the graph in the previously we checked it, 44,500 is F15, and from that we are going to consider the how the WV by W0 will be taken from the graph historical data. So that also will be known, but we have to check the fuel weight estimation as the mission starts. The fuel consumption will be occurring. So each mission segment, how the fuel weight will be considered, that one you need to calculate it. Okay, for the takeoff run, usually fuel will be burned 3%. Here we are doing according to that how much the percent of the fuel will be burned in each fuel in each segment. So when you see that W off by W naught is, we know that 1.06 minus 1.008 e to the power of RC by L by D into eta P. Please make a note of it. These are all things should be known. Already we discussed regarding this. So just we are designing with and taking with an aircraft, that is light sport aircraft. We are taking an example and we are going to design. So here you can see that 1.5% of the fuel and descent flight, during that it will be around 4 to 5%. And also we can see thus there is no fuel difference in the segment. For the landing run, we assume that 0.5% of the fuel burned. Allowance is also made trapped around 6%. By putting together all these assumptions, we write the fuel weight ratio as given, that is 1.06 minus 1.008 e to the power of RC by L by D into eta P. We can see that first 1 to 2, it is a ground run and it have a takeoff, 2 to 3 is a climb, and 3 to 4 is cruise, and 4 to 5 is a loiter. You can see that descent, and 5 to 6 is a landing. There are all 6 mission segments totally in this. Okay, just to look here, and if you have a calculator, please keep with you and it will be helpful. Okay, the range RF and light the sport aircraft is around 340 miles. How much miles should go? This is R range, and specific fuel consumption is 2.02 into 10.7 lb. That is a typical propeller efficiency is given by 0.85. All the values we have now. Okay, and W off by W naught will be calculated by using this formula. You can see that by substitute in this equation. So we have R value and L by D value, eta P. Eta P value is 0.85, fix it, and L by D is taken as a 14, yes, and C value is taken as this. You can see that, just put the values, and R value they given 340 miles. So accordingly, we just put the values and get it by the calculator. So what the value will get it? That will be around W F by W naught is equal to 0.088. Okay. So these are all the values will be given. According to that, we have to take up. So just we have to calculate accordingly. So next it is, so the first weight estimations in this we have seen it. So next we are going for, in this graph we can see that, so historical weight for light sport aircraft. There are all the different type of light sport aircraft. We have a WV by W naught, GT 500, Jabiru J160, 822 Whaler, stock S500, Ninja SR, Euroflex, and Paradise CH750. These are all the different types of sport aircrafts. Okay, so W naught as well as with the empty weight. Finish. Okay, so these are all the things. And ZA 230 is a two-seat aircraft. For simplicity, we assume that both occupants have the average of 200 lb weight, and each of them allow 40 lb. So therefore, we have a 200 lb weight, and each of them swallow 40 lb luggage. So therefore, WP is 40 lb plus 40 lb. Total will be 80 lbs. So that is the pounds. So in this we can see here. So in this we can substitute all the values in WF by W naught value also we got as WV by W naught. So total design gross weight of an aircraft is how much here? 1270 lbs. Understood? So by using the gross weight we can estimate the fuel weight as, so this is a 0.088 W naught. The 0.088 into 1270, that is 112 lb only for empty weight. Empty weight how much it is? 112 lb in out of 1270. Okay, the estimation of crucial performance parameters. So in this there are 4 main parameters that determine the performance of an aircraft. One is maximum lift coefficient, and the next is CL max, maximum lift to drag ratio, L by D max, W by S, and T by W. These are all the 4 main parameters that determine the performance of an aircraft. And maximum lift coefficient is CL max. The maximum lift coefficient depends on the selected wing airfoil. Abundance of airfoils are available for this purpose, although at this stage it is not quite critical to have a detail of the chosen wing airfoil. It is necessary for us to estimate the expected maximum lift coefficient. So therefore you can see that CLM, the maximum. So by using this, and the maximum lift to drag ratio, we already taken up L by D is 14. So we have to go back and look into that book. So whichever the how you're going to select according to that, it is a light sport aircraft. And W by S, we have a wing loading estimated based upon the 2 constraints. So how we are going to do the wing loading? One is for stall speed, another one is landing distance. Okay. So therefore, steady flight stall speed Vs is 2 by rho infinity. That is understood. We have a free stream density, and W by S is a wing loading, and 1 by CLM, that is called coefficient of maximum coefficient of lift. And requirement of specifies, we have a Vs stall speed 40 knots, that is around 67.5 feet per second, and air density or around 0.002377 slug per feet cube, and W, and we have W by S, and in this W by S we can see that, so we have, just you can square on the both the sides here, V square S, and so when you look here, 2 by rho infinity W by S, 1 by CLM. So in that, what happens, we have to calculate the wing loading just to with using up free stream density, coefficient of maximum coefficient of lift, and stall speed. Just substitute here, we are going to get a wing loading is how much, 16.2 lb per feet square. Okay, next we compute the W by S for landing distance complement constraint. The total distance you can see here. So in this we can see, that, so distance, total landing distance is composed of approach LA and LF, that is flare, and LR is the distance ground roll. We consider the typical approach angle. So in this typical approach angle for, so light sport aircraft is around 10 degree. The ground roll distance is approximately using, this is called LR. It's a ground roll distance. It's a 53.5 root of W by S. That's called a wing loading. Already we know that what the value we got it from the wing loading. So from that, so we are going to calculate, since the allowable landing distance is stated in the requirement of 1100 feet, we can compute LA and LF as allowable distance by using a ground roll. So that is 392.3, that is a feet for a ground roll. Okay, and thus we have W by S is 15 lb. So according to that, we have seen that what should be the wing loading, that is just substitute all the values for our CLM. So in this we can substitute LR value and CLM value, so then that we are going to calculate it. Okay, so W by S is 19 lb per feet square. W by S is, so is a two different wing loadings we got here. One is 19 and another one is 15, obtained from the stall speed and landing distance. So this is for stall speed and this is for a landing distance. Okay, so each and everything, the wing loading will change. Understood? So therefore, in the both the things we have to look into it. One is two different loadings. One is for stall speed, another for landing distance. Fine. And SW, W naught by W by S, and power required W by W, and 15.9 W by S, and takeoff distance 0.222 v square, v square sine of cos inverse of 1 minus 50 divided by 0.22 into v square CLM. So therefore, then the required power is takeoff with a gross weight. W naught is 1270 lb, calculated as, so we have, this is the thing, this is the required power, that is we can see 19,802.5 feet into lb per second. This is a typical propeller efficiency is given 0.8. The power of the engine should be at least, so you can see that from this we have a 1980.25.8. It is the efficiency eta p, and 550 into eta p. So we have, according to power output, we have can calculate it by the for a. So go back towards and look into in the Raymer, and we have propeller efficiency aircrafts. How we are going to take up power loading and understood. So HP by W. So now, so in this, what happens here? Next is to estimate the power required based on the rate of climb, that is 500 feet per minute. So RC is equal to, you can see eta P divided by W. So therefore minus 2 by rho infinity K by 3 CD naught W by SP to the power of 1 by 2. This is for understood. So therefore maximum RC of an propeller driven airplane can be written as, for a typical single engine airplane, zero lift drag coefficient is taken as 0.017. Understood? This is for a zero lift drag. It is called parasite drag, zero lift drag. So now L by D 14, CLM is 3.5, K allows. So we know that K by 4 CD not L by D. The value we discussed in the previous section. Okay, so what is the formula how we are going to take up? So in this we have Oswald efficiency. So 0.6 AR as follows. For light aircraft, it is reasonable to have AR that is about 1 by pi EK. So now, so accordingly we can see that. And specific consumption, you can see that we have a P is equal to RC by 2 by rho infinity K 30 T naught W by S to the power of 1 by 2, 1.155 divided by L by D, W naught by eta P. So by that, when I substitute all the values here, I'm going to get how much it is. That is 31,066.5 divided by 50, that is 56.5 HP. This is the power required. So PR, the estimation of the maximum speed that the Vmax is, how much it is? 115 knots. It is 115 knots. You can see here is a 115 knots. The specific maximum speed is assumed to be 3000 feet, and this flight phase thrust is equal to drag. So T is equal to, so you can see T is equal to drag. So therefore we know the thrust of rho v square SC to CD naught plus 2ks rho infinity v square w by s the whole square. So we can, that what is that, thrust is equal to how much we are getting, 93.2 lb. Consider propeller efficiency is about 80%, so we can estimate 80 by 100 is a 0.8 we taken up, right? We can estimate the power required to meet the maximum speed. So therefore T by eta p and Vmax, so 93 by 0.8, it is 191. So therefore we have a power required will become 40.4 HP. So this is for the maximum speed, or as follows. From the power analysis, clearly that rate of climb specification is determining factor of the required power. Always remember that the rate of climb specification is the determining factor for power from the engine, where in this case the engine should be able to produce a maximum power. So it should produce about 56.5, because during the takeoff itself we required a lot, like a larger power output is required. So therefore 56.5 HP or more. Several engines are commercially available to meet our requirement, where the most common is Rotax 582, the 65 HP. The power loading can be expressed as W naught by P. So therefore 1270 divided by 40.4, that is 31.44 lb by HP. So now we are looking for aircraft layout. In this we can see that aircraft layout. So the parameters that we have estimated so far sufficient to allow us to produce the first conceptual layout of the airplane. That is, as we progress into more details analysis, the later design stages, the layout will be revised, modified and improved accordingly. We begin with the determination of several design aspects of overall airplane configuration. There are a lot of arguments and advantages and disadvantages of certain design features. As the design process involves much of compromise, the design factor is much depends upon the on what the airplane is intended to perform. In this regards, what happens, we choose a conventional design features, that is high wing, tractor type, tricycle. Already you know that high wing configuration, tractor type is nothing but a what? Pusher is packer and tractor is front. That propeller will be fixed at the front portion, and landing gear in detail. These are all the configuration layout. Okay, so LSA design and overall proposed aircraft layout. So if this is the configuration layout of an LSA is high wing configuration, tractor type, tricycle of landing gear. T-tail configuration. Already we see that different type of tail configuration during the airfoil selection. And by using a Rotax 582 engine, so this is the engine what we are going to use it. 2 people on board. The center of gravity will be estimated around 6.72 feet location. Okay. Now wing configuration. We'll look into for a wing configuration. In the wing configuration, you can see here. So ZA230 aircraft must be able to fly at a very low speeds for takeoff and landing, and yet it must be able to offer an acceptable cruise performance. In this regards, we must be able to provide a high lift wing with the wing area as small as possible. The task is delay to the wing, so therefore higher angle of attack. So we use the common solution to this problem is, which is to add flap on the wing. So why the flap will be used? It is for it increases the surface area and it delays the flow separation. By delaying the flow separation, it gives rise to a lift to an aircraft. So that is, flap is taken as high lifting device. The chosen wing platform is rectangular with a unity taper ratio. On top of that, leading edge slat is also added to the wing, where it can prevent the stall up to approximately 30-degree angle of attack. Notice that it is a wise decision to choose the high wing configuration, because it is offer a large space of a large wing flaps lead to the high lift. So the estimated wing area is 84.72 feet square and aspect ratio is 0.6. Thus for rectangular wing platform, we have the wingspan and wing chord of 24.5 feet and 3.5 feet respectively. We use the horse fan for both the flap and aileron. Okay, and fuselage for ZA230, the fuselage is accommodate engine, people, fuel and baggage. 2 seats are arranged in the side by side. You can see that the 2 sides in this are side by side. You can see in this side by side. From the design simplicity, weight saving, the remaining fuselage section is narrowed. So new remaining fuselage section is narrowed here, okay. and arbitrarily we choose the length of an aircraft from the nose to the tail. From the nose to the tail, mean aerodynamic center is 20.2. This is a reasonable number. We compare the length of the wingspan as it has typical ratio for the light aircraft. You can see that. So this is the each and everything, the components they given up. So what you do, just take up these values and try to design in the CATIA. Okay, this is the thing what I want to give assignment. Just whatever things are there, you take all the parameters will be given here. Just to go for LSA, light sport aircraft, and this is the wingspan 24.50 and 5. You can see this is the strut what we are given up. So each and everything, all the dimensions are given. Please design accordingly. Okay, so we are configuration layout of ZN23 LSA and tails. What type of tail is we are using? We are T-tail configuration, where the horizontal tail are located somewhere on the vertical tail root and the end of the fuselage. This configuration is favored because it provides a substantially good undisturbed airflow over the horizontal tail, thus increasing the pitch control effectiveness that is desirable as LSA aircraft. Furthermore, this configuration enables to have a smaller aircraft vertical tail because the placement of the horizontal tail acts as a winglet and thus increasing of the effective aspect ratio. The tail sizing is based upon the chosen typical tail volume coefficient GA aircraft. Okay, so we can see VHT and VVT. That is a like a horizontal tail, and we have a vertical tail. Length of the horizontal tail, area of the vertical tail, and chord and surface area. So 0.7 and 0.04 accordingly. Okay, and we have a landing gear. What type of landing gear it is here? Tricycle. So tricycle configuration has the advantages of higher stability on the ground and allows the aircraft to land at a fairly grabbing attitude. For structural and space reasons, we place the main landing gear at the wing center. So we are going to place you can see that in the wing center. In this diagram, you can look here in the wing center. So where we are going for landing gear, you can see in the wing center. You can see that wing center. And so therefore, we have to know that. So and we have a better weight estimations. We have, so now we already have the configuration layout of the aircraft, but having the layout, we can have a better weight estimation when compared to the method used in the section 3.0. This method is also based on the historical data. Due to this, but it is referring to the aircraft layout, which is actual shape size of the aircraft. The estimation of the major aircraft components are approximated from certain ratios as given. Based on the aircraft shown, we need to calculate the exposed wing and tail areas and fuselage wetted area. So the calculation of the wing and tail areas is quite straightforward, but we need to simplify the fuselage shape in order to calculate the wetted area. So therefore, we know that already we have a WV by W naught is 0.55. So therefore, WV by W naught is 0.5xx, and also we know that 1270 lb and 6 is equal to 698 lb. As expected, we have an empty weight reduction about 5% when compared with the weight obtained by a previous crude estimation. Okay, so again we can check here. So total is 200 is the crew weight, payload weight is 80, and fuel weight is 111.76, and empty weight is 6665.1 lb. Okay, so we can see that. Please, we have a multiplier factors here, an estimation of the empty weight. Wing weight 2.5 into exposed wing, horizontal tail. We have exposed horizontal tail at 26, vertical tail, and we have a fuselage weight, a landing gear weight, an installed engine, and all else empty. So all these we have total empty weight is equal to 665 lb. So already in the center of gravity when we are calculating, I told you what should be the empty weight. So therefore wing weight. So all the things when I make it, so we are getting a 665 lb. So why it is 2.5 exposed wing? So we have to check accordingly. 2 into exposed tail weight, understood, tail area. So next we can see that in the iteration for gross weight. So we are going to the iteration from the 665 it is started. If I put gross weight, it is 112, 1250. 663 if I put, it will be around. So now note that weight estimation will continuously get improved as we have to later stage the design process. This is the apparent, because we know that actual components to be fixed on the aircraft, the corresponding weight build-ups as most accurate. You can see the performance analysis. So wing loading and W by P. In this we can see, or in this we can see. So we have 14.8 and 31.0. That is the wing loading and power loading. So two things here. W by P is a, and VS. That is the stall speed. So stall velocity is 38.9, and the LA. So when I substitute 976 feet. So according to that, when I substitute here, LF, LR, rolling distance, 396 feet already we have discussed regarding this. And also the center of, like, we have a gravity, acceleration due to gravity 32.2 feet per second square. Rho is the air density at the sea level, and mu is the typical ground friction coefficient. The approach theta a is taken as 3 degree for typical value. The landing distance about 1417 feet. We satisfied the landing distance requirement as it is stated in the specification that landing distance must not greater than 1500 feet. So we should not go beyond the 1500. Okay. The height angle should be 20 degree. So we have to take all these considerations before. So now, and LEA. So what we are concluding from this is, so we have discussed the essential steps to develop a LSA design. In the conceptual design stage, the analysis are clearly presented and discussed methodologically. It started with a set of the requirement, and then based on the historical data of aircraft on the similar class that we are intended to design, we select the most appropriate empty to gross weight ratio. From here, we can make the initial estimates and several important performance parameters. Then the aircraft layout is proposed. Okay, this is followed by better weight estimation based on the sizing of the aircraft. Finally, the better weight estimation guides us to calculate uh, though the most meet performance criteria, since a lot of improvement needed to done on the analysis, such as calculated takeoff distance is for exceed the requirement, optimization is needed for analysis, and this is left for future work. In this context, we may redesign the aircraft in order to increase the takeoff distance, where this may be possible by having lower lift coefficient. Consequently, having a lower lift coefficient is simply using a more simple and of course less cost. So therefore, these are all the different type of understood. So this is the complete, and also you can just look into the Ramo book. By this, wherever we taken from that, we are going to design, and also you can references. We can go back with a and study about history of technology, and we have design of aircraft, aircraft design, and conceptual approach by understood Ramo. Also each and everything. Just please go back and look into it. You'll be understanding. So if you have any doubts, please text me, and just I will get back to you regarding this. Okay, understood. Fine. Okay. Okay. Thank you.